Today we are going to study the topic bar magnet as an equivalent solenoid from chapter 5 Magnetism and Matter. The field lines of a bar magnet and solenoid are similar. In the case of bar magnet, we can see that outside the magnet, field line starts from north pole and ends on the south pole. Inside the magnet, they start from south pole and ends on the north pole. They are continuous loops. Now, if we consider the case of a solenoid, the loop on which current flows anti-clockwise can be considered as a north pole, and on the other end where current is clockwise can be considered as a south pole. We can see that field lines of a solenoid is similar to that of a bar magnet, that is, they start from north pole and end on south pole outside, and inside they start from south and end on north. So, the field lines of a bar magnet and solenoid are similar. So, here we have a solenoid of length 2L. So, this point is minus L, this is 0 and this is plus L. We are going to find magnetic field at a point P at a distance r from the origin. We have taken a small element of thickness dx. It is at a distance x from the origin. Now we are going to use this equation. This is the equation for a circular loop of radius a, and P is a point at a distance x from the loop. Then field at P dB is equal to mu 0 I a square by 2 into a square plus x square raised to 3 by 2. Now we are going to use this equation to find magnetic field due to this element dx. Let us call it dB. So, in the denominator we have mu 0 I a square. This equation is for one turn. Here in this small region dx we have n dx turns, that is, number of turns per unit length is n. So, number of turns in length dx is n dx. In the denominator we have 2 a square plus r minus x the whole square raised to 3 by 2, that is, instead of x, the distance of this element from P is r minus x. So, here we have r minus x the whole square raised to 3 by 2. Now, we are going to take r square to be greater than both a and x. So, a square plus r minus x the whole square is approximately equal to r square. Now, substituting this value in the denominator, we have mu 0 I a square n dx by r cube. Now, we are going to divide the whole length from minus L to plus L into small elements of thickness dx and find dB for all the elements. On integrating all the dB, we get the total magnetic field B. So, B is equal to integral dB from minus L to L. Here we have substituted value of dB. Now, we are going to take the constants outside. Mu 0 I a and n are constants. In the denominator 2r cube constant. So, inside the integral we have minus L to plus L dx. Now, integral minus L to plus L dx is equal to x with limit minus L to L. On giving the limit for x, we have L minus minus L, that is 2L. So, B is equal to mu 0 n I a square by 2r cube into 2L. Now, we are going to multiply and divide the numerator and denominator with 2 pi. So, on the denominator we have 2 pi here, and the denominator we have substituted the 2 pi with 2 to get 4 pi. Now, here we have 2, then n into 2L, then current I and pi a square. Now magnetic moment M is equal to number of turns into current into area. Here number of turns is N into 12. N is the number of turns per unit length. For length 12 we have N 12 turns. Current is I and area is pi a square. So these terms together we can write as magnetic moment M. So B is equal to mu 0 by 4 pi into 2m by r cube. This is the same equation that we get in the case of a bar magnet at a point at a distance r from the center of the bar magnet. So the bar magnet can be considered as an equivalent solenoid.